Hi guys, welcome back to my channel. So we're going to be going over parameterizing curves, and specifically we're going to look at lines, circles, and ellipses. So remember that parameterizing means you're going to be looking at your x and y variables as separate variables dependent on a parameter, which is generally going to be either time or an angle depending on what suits us. So let's take a look at parameterizing a line. Specifically, let's look at the line segment between 1 and 1, -1 and 10, -5. So we're going to be starting at 1, -1, stopping at 10, -5. And knowing that this question does not ask us to have a specific time value, our time is our choice. So we're going to just choose, my favorite is to go between 0 and 1. So we're going to let our parameter range from 0 to 1. And once we make that choice, there's a pretty easy pattern to help us write our x and y as functions of time. So we're traveling in a linear path, and because of this, you can start with your starting x coordinate, which is 1, and your ending, and then it's kind of like having almost a binary switch. You turn off the 1 with a 1 minus t, that'll turn it off at time equals 1, and you can turn the 10 off at 0 by writing a t. So when you add them, you now have a linear combination of time values between 0 and 1, and what it's doing is it's basically scaling the 1 and 10 so that you travel from 1 to 10 as your t ranges from 0 to 1. So repeating the pattern with a y, we start at -1, we end at -5, and starting with a 1 minus t, and ending with a t, we add, and then this is a completely fine parameterization, or you can simplify and you end up getting 1 plus 9t, and when you simplify this one you end up getting -1 plus, looks like -4t. Okay, and then making sure to just write our parameter value. There's our parameterization. Okay, let's take a look at a circle. So I'm going to make you guys think back to your trig days. We are parameterizing a circle that goes clockwise, has radius 2, and it is centered at the origin. So if we look at our graph of this circle, it's basically a scaled up version of our unit circle. So our unit circle would have radius 1 because it's called a unit circle. And this circle has radius 2. So it looks, something like that. And it's traveling clockwise. So that's different than the unit circle, which generally travels counterclockwise. So to remind you what our unit circle would be, our unit circle has the equation x squared plus y squared equals 1, and you go counterclockwise. Versus this circle is going to have the Cartesian equation x squared plus y squared equals radius squared, which is equal to 4 because our radius is 2. So then dividing both sides by 4, we get maybe the more standard equation for a circle, which is to have it equal to 1 on the right. So that's the Cartesian equation for this circle, but we want to have x equals and y equals separately. And since we're working with a circle, it might be helpful to also note that the unit circle, how does that relate to cosine and sine? The x coordinates are cosine theta and the y coordinates are sine theta. So that's actually a parameterization of the unit circle in terms of angle. So keeping that in mind, let's start with kind of an educated guess that x is a cosine theta and y is b sine theta. And let's pretend we don't really know what a and b are. We'll figure it out. So plugging that into our equation for this particular circle gives us this equation, a cosine theta squared over 4 plus b sine theta squared over 4. Simplifying that, you get a squared cosine squared theta over 4 plus b squared sine squared theta over 4, and that should be equal to 1. Now hopefully you guys can look and identify what's problematic. Our equation would basically be true as long as this a squared over 4 and b squared over 4 was gone, right? What we want to have is just cosine squared plus sine squared, because cosine squared plus sine squared theta equals 1 based on the Pythagorean identity. So knowing that, that tells me that I want my a squared over 4 and my b squared over 4 to be equal to 1. So that means that a and b would both have to be equal to 2. Okay, so verify. Look at that equation for a second. When I have a equals to 2 and b equals to 2, when I plug it in, it'll get canceled by the divided by 4, and then we'll just have cosine squared plus sine squared equal to 1. And my equality checks out. Okay, so keeping that in mind, we're going to have 2 cosine theta and 2 sine theta. Okay, but this would be generating it counterclockwise. So you can either adjust your theta values, or what I think is a little bit easier is to just travel the circle backwards. So instead of using thetas, let's use a negative theta. That tells the circle to go backwards through its angle. So we can simplify that, which your textbook would do. Your textbook would say that this is equal to 2 cosine theta because cosine is even, and this is equal to negative 2 sine theta because sine is odd. Okay, and that simplification is just assuming that you know your trig really well, basically. So lots of times the calc textbooks will just kind of take it for granted that trig is really rock solid, and they'll do things like that without really saying why. And our theta values, remember, we're traveling between 0 and 2 pi. So there's our parameterization. Let's take a look at an ellipse centered at the origin with major axis length 12 and minor axis length 2 on the x and y axes respectively. And it's going to be generated counterclockwise. So our picture for this would be centered at the origin. We're counting out. The major axis just means it's the longer axis, and it's happening on the x-axis, so you go 6 units left and right because the full length should be 12. And then minor axis is on the y-axis, and it should be 1 unit. So here's what our ellipse looks like. Doing my best to draw a nice oval. Fell a little bit short there, but it's okay. Just trying to get an idea. This one is generated counterclockwise. And thinking back to our conic section study, because we're centered at the origin, we still have x squared plus y squared, but our values under the x squared and y squared are going to be different. So it's going to be over 36 for the x, which is the 6 squared, and it's going to be 1 squared for the y. So to get those numbers, you count out from your center to one of your points on the conic and square it. That's basically how it goes with the Cartesian equation. Now, where does that come from? It actually comes from the parameterizations. It's kind of like a circle, like what came first, the chicken or the egg. So right now we're trying to get to the parameterization. So we need to know about the Cartesian coordinates for it. So using what we know about circles, the ellipse is kind of like a circle that has 2 different radii. So I have a speculation that it's probably going to end up being 6 cosine theta and 1 sine theta, but we'll play dumb a little bit here and just see how it works out with our algebra. So if I have x equal to a cosine theta and y equal to b sine theta, and I plug that in, I get a squared cosine squared theta over 36 plus b squared sine squared theta over 1, and I need that to be equal to 1. So in order for it to actually be equal to 1, I need my a squared over 36 to be 1 and my b squared over 1 to be 1. So that would mean that my a should be 6 and my b should be 1. Okay, and since we're generating this counterclockwise, that's the exact same direction that the unit circle goes, so it means that our theta ranging from 0 to 2 pi will take care of that direction for us. So 6 cosine theta and 1 sine theta, and our theta ranges from 0 to 2 pi. There's our parameterization. Okay, so hopefully that helped explain to you guys a little bit about where all those parameterization identities come from, so that in case you forget, you still have some idea of how to go about doing this. See you next time.